In this session, I will discuss determination of wing designing parameters. The first parameter we have is wing incidence. Figure A shows wing incidence, which is the angle between fuselage center line and wing chord line at its root. It is also referred as wing setting angle and is denoted as alpha set. The wing incidence design requirements match with wing airfoil angle of attack corresponding to airfoil ideal lift coefficient. As the formula for wing ideal lift coefficient is discussed in the previous session, by solving that equation, wing ideal lift coefficient is calculated. Then by the reference graph as shown in figure B, which is CL versus alpha, gives wing setting angle alpha set, which is corresponding to the airfoil ideal lift coefficient CLI. The table on this slide shows the values of wing incidence for several types of aircraft. Next parameter is aspect ratio, denoted as AR. For rectangular wing, aspect ratio is the ratio of wingspan B to the wing mean aerodynamic chord MAC or C bar. That is AR equals B divided by C bar. For tapered ratio, aspect ratio, for tapered wing, aspect ratio AR equals B square divided by A, where A is wing planeform area. For general planeform, mean aerodynamic chord is determined by C bar equals 2 divided by S integration of 0 to B by 2 C square Y dy. For tapered planeform, mean aerodynamic chord is determined by C bar equals 2 by 3 CR into 1 plus lambda square divided by 1 plus lambda, where lambda is taper ratio, C is local chord, Y is lateral axis, and CR is root chord, and S is wing planeform area. Here the table shows the values of aspect ratio for various types of aircraft. Next parameter is taper ratio. The taper ratio is the ratio between tip chord CT to the root chord CR. That is lambda equals CT divided by CR. This definition is applicable to wing horizontal tail as well as vertical tail. In general, taper ratio value varies between 0 and 1. For rectangular wing, the taper ratio lambda will be equal to 1. For tapered wing, the taper ratio will be between 0 and 1. For delta wing, the taper ratio will be 0. The table on the slide shows the values for aspect ratio and taper ratio for various types of aircraft. Next parameter is sweep angle. The figure shows 5 wings with different sweep angles. In this figure, the dotted line is the fuselage center line and this y-axis is the lateral axis, which is perpendicular to the aircraft fuselage center line. For the A wing, there is no sweep angle. For B wing, the angle between the leading edge of the wing and y-axis is called leading edge sweep angle. For C wing, the angle between the 50% chord line and y-axis is 50% chord sweep. For D-wing, the angle between wing quarter chord line and y-axis is referred as quarter chord sweep. Lastly, for E-wing, the angle between wing trailing edge and y-axis is referred as trailing edge sweep. Low subsonic aircraft, where aircraft maximum speed is less than 3, no sweep angle is required. For high subsonic and supersonic aircraft, sweep angle can be determined by using the formula mu equals sine inverse 1 divided by n. Sweep angle equals 1.2 into 90 minus mu, where mu is Mach angle and n is aircraft cruising Mach number. The table shows sweep angles for several high and low speed aircrafts. Next is twist angle, denoted as alpha t. When the wing tip incidence and wing root incidence are different, the twist is called as geometric twist, as shown in figure 1. The wings having different airfoil sections along the span with different values of zero lift angle of attack is called aerodynamic twist, as shown in figure 2. The criteria and limit of wing twist is formulated as alpha t plus IW should not be greater than or equal to alpha naught, where alpha t is twist angle, IW is wing incidence, and alpha naught is zero lift angle of attack. Both geometric twist and aerodynamic twist have advantages and disadvantages, where the designer must decide which one to select that satisfies the designing requirements. The amount of twist is determined through calculations. The application of aerodynamic twist is more convenient than geometric twist. The problem in the application of geometric twist arises from manufacturing point of view. The table shows geometric twist angles for various aircrafts. The table on the slide shows aerodynamic twist angles for various types of aircrafts. Next parameter is dihedral and unhedral angle. Angle between chord line and XY plane is called as wing dihedral angle. If the wing tip is higher than the XY plane is positive dihedral angle, as shown in figure A. If the wing tip is lower than the XY plane, it is called as negative dihedral or unhedral angle, as shown in figure B. Typical values of dihedral angle lie between -15 and +10 degree. Wing dihedral angle improves the lateral stability of the aircraft. Due to the aircraft symmetry, both right and left wing have same dihedral angle. Lateral stability means the tendency of aircraft to return back to its original position if disturbed by gust and roll around x-axis. Lateral stability is also called as dihedral stability. Shows typical values of dihedral angle for various wing configurations. Table 2 shows dihedral and unhedral angles for various types of aircraft. Next is lift distribution. The distribution of lift per unit span along the wing is referred as lift distribution. Entire area of the wing span produces specific amount of lift. The total lift is the summation of all these individual lifts. The figure shows front view of wing with elliptical lift distribution. The horizontal axis represents y by s, where y is location in y-axis and s is semi-span of wing. In this figure, no high lift device, say flap, is deflected and also fuselage effect is ignored. CL goes to 0 at the wing tips due to high pressure airflow from bottom to the top of the wing at y equals minus b by 2 and plus b by 2. Thus, no lift is generated at these 2 points. The major application of lift distribution helps in aerodynamic calculation of wing. The wing tends to stall. The wing root stalls before the wing tip, which means CL root will be equal to CL max and CL tip is less than CL max, and the lift distribution, as you can see, is elliptical over the half wing as shown in figure 1. Figure 2 shows the wing tip stalls before the wing root because CL max is nearly equal to CL tip while CL root is very less than CL max, and you can see the lift distribution is also non-elliptical. Is load distribution of lift distribution times sectional chord, that is C dot CL, along the wingspan is referred as load distribution. The bending movement at wing root is a function of load distribution. If the load is concentrated near the root, the bending movement is less. The elliptical load distribution is close to the wing root. This leads to lower bending movement at the wing root, as shown in figure A. If the load is far from the root, the bending movement is more at the wing root and the load distribution is non-elliptical as shown in figure B. Load distribution is a function of lift distribution. The major application of load distribution is in wing structural design. Both lift distribution and load distribution influence the aircraft performance, airworthiness, stability, control, and cost of the aircraft. Ideally, both lift distribution and load distribution are preferred to be elliptical. The principal goal in wing design is to obtain elliptical lift and load distribution without considering contribution of fuselage, flap, and other components. With this, I will end up this session here. Thank you.